So we talked about two hyperparameters. There's an epsilon, which is measure the distance. Then there's an endpoint, which decide how many points make the identification of a in or out. Okay. The concept of the distance function can play a huge role as well.
Absolutely.
What would be the distance function?
Absolutely. So that is an implicit third hyperparameter.
Okay. That's always assumed for the clustering algorithm.
That is right. In fact, the next topic after telling you about DENCLUE is precisely the deep implication definitions of distance have. We'll come to that.
Okay.
All right, guys. So I will now get into an algorithm that is called DENCLUE. And I like it because it makes, once again, an argument that is so classical, theoretical physics kind of an argument that you absolutely love it from the moment get-go. So it basically says, I'll give you an intuition here. Imagine that we have just had Diwali. So I'll use Diwali as an intuition for this thing. So Diwali, for those of you who don't know, is, I suppose most of you probably do, is a festival of lights. What people do is they light up a lot of lamps, little lamps, oil lamps. So just the background, let me just say, because I'm going to use this. And obviously, we just had Diwali 2 days ago, 3 days ago, Thursday. So Festival of Light, lots of oil lamps. Right. So imagine a little oil lamp. Typically, you represent it like this, and it sheds light. It is shedding light at a given point. So this is the point at which you imagine there's an oil lamp. You would agree that the light at any given point X, let me take a point Xi. No, this color is not visible. But let me just use this. At a point Xi is proportional to, it will decrease with distance, isn't it? The further you go, so suppose this distance is D, right? The further you go, the less the light you will get at point Xi, isn't it? Except that there, the amount of light is 1 over x squared, but we won't use 1 over x squared. But that is the basic intuition. What you say is that based on this intuition, you imagine this intuition that from this point, let me just call it x naught. Sorry. The force, the amount of effect at xi from the point x naught, right, is equal to some decay function. And in fact, the decay function that you take, because Gaussians are so helpful, and I am being sloppy, guys, so I will remove some proportionality constants and so on and so forth. So forgive me for not putting all sorts of proportion. But what is this? E to the minus d square, how will it go? Will it go like this, e to the minus d square? Would you agree that this would be the shape of e to the minus d square? As d increases, it is basically a bell curve, half the bell curve, isn't it? Do we all agree with this? Right? So yeah. This is it. It's a good decay function that we have. Now that we have this decay function, we now take this intuition. Suppose you have 5 points, x1, x2, x3, x4, x5. Right? And you have another, or maybe I'll just make it x6, and let's say x7. And then you have another points, x8, x9, x10, x11, x12, x13, x14. Are we together? Now, and then maybe there is another point here, x15. So what you do is, and now let me just separate this area out so you can focus here. Um, let me do one thing. No, actually, forget it. So are these points clearly visible, guys, on the screen?
Yes, no problem.
No problem, right? So you take an arbitrary point in space. So let us say I take an arbitrary point. What should I take? Let me take here because I don't have to stretch my hand too much. X, right? You realize that from this, I will get, I'll get the influence from every single point, including this, all these points. I won't draw all these points, but from all of these, so I can say that given this point X, I can have fxi x I can have, right? At this point, I will have the light coming from, in some sense, well, light doesn't decay as a Gaussian, but imagine some funny light. The field, the technical word people use is, it's a scalar field. Or think of it as an influence field. And I believe that's a word people do use for this. Influence field. The influence at the point X is the influence coming from all the points, isn't it? That are there in the data instances. Are we together? Right. So I can write the total influence, and I forget what exact notation people use, but let me go with my own notation. F, the total influence at the point X is just a function of where you are, right? Depending on, in this feature space, the total influence as a sum of all the influences, it is a function only of the point where you are sitting, isn't it? Because data points are fixed. Does that make sense? Or did I lose you guys? So imagine that the amount of light at this point X, if you think, is the sum total of light coming from all the little lamps. The brightness at the point X, how illuminated point X is, it is based on how much light it is essentially gathering or getting from each of the little lamps. If you're trying to read a book there at point X, you're being helped a little bit by the light coming from all these little lamps, isn't it? And so the total light at that point, in a metaphorical sense, is the sum total of all the lights from these little lamps, right? It is this. Would you agree? And if you go to some other point Y, then maybe you're further off and you may get a different amount of light there from the lamps. It's common sense. If you go too far away, then it gets even less. Right? So, or think of it as a heat field. The further you go, suppose each of these were sources of heat, you would agree that if you want to get warm, you better be close to the sources of heat. The further away you go, the less the heat.
Or effective gravity.
Or you could think of it as gravity. See, all of these are, take it metaphorically, because in a very technical sense, the decay rates are 1/r² and things like that, right?
Is there a directional component?
No direction component. That's why, yeah. So this is important. No directional component. No directional component, right? That is why we say it is a scalar field. Scalar field. Now, what is a field? This word, this is one of the most beloved words of theoretical physicists. Field. The moment you hear field, we light up like a bulb, right? So what is a field? A field is actually any function that takes value at every point in the space, right? So given a space here, a feature space, if you can have a function that will have a definitive value at every point in that space, in a very rough sense, that is a field. I mean, they can have a more jargon-filled definition, but that's a good intuition for it, right? So think of the light or the warmth at this point X coming from all these little lamps. That should be good enough, right?
So these are not like directional antenna.
There is no directional antenna to it. There's no directional antenna to it. It's like heat, when if you have two fireplaces here, you're getting heat from both. You're just getting warmed. That is it. Heat is a scalar field. Scalar means it's a number. Temperature is a number. right? Luminosity at a point, like how much light you're getting. Ambient light is a number, just a number.
So if you take the centroid of those gears and you draw a circle around
No, no,
it.
don't do centroids. Forget it.
No, but
So
what I
don't.
meant is that radius all around it, you'll get the same light everywhere. It's going to be.
We're
the same
getting
light.
there, not exactly. Just hold on.
Okay.
Now, hold on to that. It's a little bit more subtle than that,
Okay.
but just go with that. So we do understand scalar fields, no directionality. It's just a net warmth, right? Albert, go ahead.
So field and space is the same. Why call field two different words?
No. Space is just the coordinates, the feature space. No? But at each feature space, there is a measurable value like temperature. If all of these are lamps, at different points in the feature space, there'll be a different amount of heat that you're receiving. So a field is different from space itself. Space is the geometry, it's the container. But at each point of that space, there is a measurable value. That measurable value together forms a field. Right? So now comes, and you would agree that that is a function purely of x. If all the data points are frozen, if all the lamps are frozen, you agree that if I move from here to there, and if I were, let's say that these are lamps and you're trying to read a book, you go far off, you won't be able to read the book. You come closer to the lamps, you'll be able to read the book, isn't it? So far, so good, guys. And now comes a very interesting thing. We use an argument, which is the opposite of gradient descent. It is called the hill climbing. Hill climbing. What does it say? So suppose I'm here. At this point, let me just call this point A, which is the point X. I feel that I'm not able to read the book. What should be my intuition? I want to go towards more light. So how would I go towards more light? I can look at, what is the path of steepest? What is the shortest path to more light for me? It would be, you would agree, remember we learned about the gradients. The path of greatest increase of a function is along the gradient, isn't it? So my x next should be where? Should be at x plus some epsilon value times the gradient of the function. Do you see this? This is where I should go. So, well, if you really think about it, and now let's ponder over what path that would be. So you realize that there are multiple forces here. One force is pulling it this way. Another force is generally pulling it in this direction. Another force is essentially pulling in this direction, right? And so the net gradient, if you really look at it, it will be a path that may basically take it. Let's try to make a path. I don't know what it will be. So I'm just guessing that you would go straight to, you would end up here. Because if you sit in the center of all of these lamps, this is your shortest path to go to a good place to read your book. Would you agree?
Yes, sir.
Right? This is it. So you will keep on finding, you'll keep on making little steps and you will go there. I'll try to create a visualization of this, guys. Huh? I'll try to, so you can see it in a very interactive way. In real time, you can see, you can build a cluster and you can see how this hill climbing takes you to that. So when you end up here, a point at which the gradient vanishes, what will happen at this point? When you have reached a maxima, what will happen to the gradient? Zero. So such a point is called an attractor. It is an attractor for this field, influence field, right? And likewise, if you happen to have started your journey, let us say here, somewhere here, where would you end up? Where are you most likely to end up? You are most likely to end up somewhere here. Yeah, maybe right on top of X3 or near it, somewhere here, right? Which would be at the center. And remember, guys, when you end up here, you don't necessarily end up on an instance of the data, but near it. Like the point of maxima may not be literally one of the existing data points. right? So this also is a attractor.
So will there be multiple attractors over there?
Yes, that is the whole point, that in your data set, start at random points and keep going there to the attractors. And once you get to an attractor, so you can do a subtractive process. See, what you can do is once you find an attractor, that you can assume, you just intuition shows you that attractor is the center of a cluster, isn't it? Would you agree that your attractor points are the centers in some sense of the cluster? They may not be the centroid, but they are the centers, places of most intensity for that cluster, right? And so what you can do is, suppose you start from a point, you find one attractor, and then all you have to do is you have to look at a certain density level, like density is again how many points there are in the neighborhood. So you can take a certain radius or area of density, a threshold of density. You can take a threshold of, let me just write it here, a threshold of density beyond which you have a cutoff, so you can draw your circle. So when I draw this red circle and pink circle, I just said that beyond that, it becomes too thin. The points are too thin, they're too few points, right? So therefore, you have your cluster. Take that cluster out and its points out. Then again start somewhere and see where does it take you. If you take the pink cluster out, then you start at A, well, you'll end up with the red cluster, right? And so gradually you'll discover all your clusters. What remains? Whatever remains are outliers, right? So whatever remains are outliers. Now, why is this a powerful argument? It's a very, I like this argument because to me, of all of these things, what I like is that it is so straightforwardly driven by intuition, by mathematics, clearly, and an intuition of a force of an influence field, that first of all, you know that it will converge. You will go, you'll soon discover the clusters, isn't it? Do you notice that there is no notion of epsilon neighborhoods and so forth, right? The only hyperparameter is like at what level of thinness do you say, okay, now I'm beyond my cluster? How do you define the boundary of it? That is not a big, like it doesn't completely change your definitions of clusters. At most, it may change the definitions of your outliers, isn't it? Right? So that is a big, those of you who are on Zoom, are we getting the point?
Yes, get the point.
Yes.
I just have one question just for understanding's sake. Instead of circle, like, is there a way, for example, if you have a bunch of lasers sitting in an arc, okay, and then you want to find the center of all those laser points where you have the maximum intensity, is it something that this kind of algorithm can solve?
Yes, in fact, the beauty of a DB scan, as we will see in the lab in the afternoon, is these things don't have to be globular, like circular. Like you can have data like this, one like this, and another one like this, let's say. You notice that, and these may be two different clusters. These are called, this is the classic half moon data set. The beauty of density-based clustering is it will actually be able to tell them apart.
Oh, nice.
Right? It's a big strength actually, that it deals with all sorts of shapes very well. The other point with DENCLUE is, do you realize that to cluster, to find the attractors, you don't have to do the computation with all the points. You can take a reasonable sample of the points and do this exercise, find the attractors, isn't it? And then assign all the points to the nearest attractor.
So
okay.
The point is actually an influencer in that attractor space. Like you say that you go with the points, right? You could have picked one point which was far away.
Yeah.
Which is not part of that cluster.
Yeah.
And still throw it away, assuming that it's.
No, one point is not. See, what happens is that this is why you say that. See, I started A. I ended up with this cluster. By throw away, I just say, now forget about it. Like, don't think about it when you start at another point.
Keep it aside.
Keep it aside. That's all it is.
Not no longer part of the computation.
Yeah.
What I'm saying is, if you took a point which was not close enough to this piece, but it was additive, but it's kind of an outlier, but yet still included as part of the
Yeah,
the part is you do the f of that sigma function, right? So you
Right.
cannot, or do you have to individually go through each point and iterate and make sure they're adding into the light? That's what I'm trying to understand.
so look at the point Y.
Ah,
You're asking about the
yes,
point
correct,
Y.
correct.
See, point Y no, will remain once you have found all of the attractors and drawn your circles around
No,
them.
I'm saying like if that y was somewhere close by over here, but far away from this piece, how do you know that you, whether you should include y or throw it
Okay,
away?
yeah, this is it. So let me make a point Z here.
Right,
Z.
that's
So
what I'm-
the thing is, okay, so how do you determine the radius of your thing? The way you do that, not the radius. What happens is you keep going out to the boundary, and at each time you ask, what is the density here?
Oh.
And density essentially means, in a way, you make a epsilon neighborhood and see how many enough number of points are there or not. Right? So once it becomes too thin,
Oh.
right, you say, I'm not going to include. So if your density is very low, then Z will get included in that cluster.
Hmm.
If your density that you need is very high, Z will not get included in the cluster. And so that is the only hyperparameter in the
Oh,
model.
I see. That's the gating, the density.
That is the
gating part.
Density is the gating factor, right? So based on how dense it is, yeah. So it is, again, think galaxy. At some point you say, right, I've reached the edge of the galaxy. And now the intergalactic cloud is too tenuous for me to really consider it as this region to be a part of the galaxy. So you need to decide some cutoff, isn't it? That's pretty much it.
Could you, I don't know if I missed it or like, so there are two concepts that you described here, right? One concept is trying to find out the influence of different points on a point.
Yeah.
And intuitively, that will arrive at possible clusters that exist.
You find attractors, you'll discover all the attractors, and
Then the
implicitly
second
around in attractors, you can now draw a region
that part
of
you-
dense points.
I don't know if you double click on that.
Okay, so
How
what you do is,
identify what is
Yeah.
the zone.
so what you do is, you can keep sort of creating one intuitive way, one very intuitive ways. Think of a certain density in your mind, right? That the number of points per square inch should be at least this much, or per square, whatever unit must be this much. Now start from the center and you start making regions and say, have I become too thin? If I become too thin, I'll stop. And that's all it is.
So, sir, how it improves over DB scan?
How does it improve upon DB scan? See, first of all, there are multiple ways. Because there is no sensitivity to strict sensitivity to epsilon, right?
But it still has a hyperparameter.
It has a hyperparameter, like at what density you stop. So now the point is that point is valid. The point is, yes, that hyperparameter remains, and that is at the heart of what you define cluster, or how much dense is still good enough for you. It often comes from the domain, but that remains a weakness. It is not sensitive, but the clusters that you get, at least the main clusters, are not sensitive to what you chose as your density, as your hyperparameter. Only the outliers are sensitive to it. So for example, this point Z, is it an outlier or not depends upon what is your cutoff of density. You got that, right?
Right.
So that is the only sort of an aspect. In practical terms, it doesn't hurt you that much because you are searching for the clusters.
I see. And computation wise, to me, it seems it is same as DB scan.
Very, it's very cheap. It is lightning fast. Why? Because I don't need every single point. I can just take a sample of points and still do in my influence field, right? Once I have an influence field, all I have to do is hill climbing and find the attractors. Once I've found the attractors, you realize that I'm done. You make a certain region around the attractors. Any points that fall in the region belong to that cluster, to that attractor.
Correct. Oh, that way it is exploiting the gradient descent pretty well.
Exactly. It exploits that. In this case, you would say gradient ascent.
Right.
Hill climbing.
Ascent, yeah.
Hill climbing. It exploits the hill climbing and the fact that you have a field here and does it. So one of the things that you'll find, scikit-learn doesn't have an implementation of DENCLUE. Right? So I give it to you as a project. Try implementing DENCLUE. Do you see how simple the idea is? or try implementing DENCLUE. I'll give you a hint, guys. You'll be able to implement it in some 60, 70, 80 lines of code. It won't be the most optimized, super optimized code. So for example, Google had a paper long ago, DENCLUE 2.0, which was highly optimized. Then later on, there were further works. I remember seeing a paper in 2016, which was about DENCLUE hybridized with expectation maximization and things like that. So there are many such bits of work done, but just do a plain and simple implementation of DENCLUE. Take this as a project, see if you can do it. And just to bring these ideas home, I'll try to create an animation so that you can literally see that if you just throw a data which has clusters, and you start at a random point, you can click at any point into dimensions and then see how it takes the path of how the force field looks, how the sort of influence field looks. Right, and from that, see, scalar fields, I typically think of them as potential fields. So how the potential field looks and how do you go from there to its maximas or the so-called attractors. Yeah? Makes for a really nice way to bring the thing home. Intuition, animation is called for. I need to sit and do that. I'll do that. Isn't this elegant? Anybody else feels that this is far more elegant than we were doing?
Is that we have to calculate the field at every point?
No. Yes and no. Yes and no. See, what happens is that you end up with a function like this, right? You realize that you have a function like this. So at any given point, all you need to know is to compute the gradient there. So you don't need to find the field everywhere. You need to find a field at some point and then start climbing the hill from there. You randomly take a point. You don't need to find a force field everywhere. So long as you have a function that you created it, start randomly somewhere, and all you need is a force and its gradient. See, what are the two things that you need here? This and this. Isn't it? You need this. If you look at this equation, where is our hill climbing equation? Look at this, right?
Once a particular hill is found,
that's your attractor. The top peak is the attractor.
then we have to like ignore those surrounding.
You can sort of. You don't even need to ignore. If you don't want to ignore it, don't. But go randomly sit somewhere else, right, and do it. See what happens. The beauty of this is that one intuition that I'll give you is at the top of the hill. Think that there is a lighthouse. You're searching for the lighthouses. Well, I'm mixing up my lamps now with lighthouses. Right. So.
This is second concept. So attractors are easy to understand.
Yeah.
The center of the attractors are also easy to understand because that
No.
point at which the gradient is zero.
Attractors are the centers of the clusters.
So
they are the points of maximum brightness. If you think in terms of light, just the most well-lit point. Where can you read the book, your book, brightest light? That is your attractor.
we got to that point.
Yeah.
Then comes in the data set, there will be multiple attractors.
Yes.
What we haven't discussed is the intuition of after I find one,
Yeah.
how do I go looking for the remaining, and how do I know I have found all?
Yeah. So then comes like technical details. One way that I do, like, I don't know if there's a,
Randomness is needed.
yeah, you start at different places and you can then find it. The other way that I do, in fact, I don't know if that's absolutely the correct way. Right? What I do is once I found an attractor and its cluster, right, I basically take it out of the equation and start all over again.
Okay. And then how do you get closure on have I found?
Ultimately, what will happen is you will be left with little points, which, so what happens is suppose only y point is remaining, right, in your data set. So what happens is you'll gravitate to y, but then you look at the density around y, and what will be the density around y? 0.
The closure is based on some kind of a sparsity of the remaining.
That's right. All because you know that you're left with just outliers. That's the way I do it.
Asif, I'm still not understanding what the big F function is. Like I get how the process works, but I don't understand what that function is.
Okay, let me repeat that. I'll repeat this, guys, once again. So suppose that, and again, guys, I'm using the word light, but as a physicist, I cringe because light goes 1 over r squared. The helium. Imagine that this is a little lamp. This is a little light, right? X1, source of light. This is X2, source of light. X3, X4, these are all sources of light. You would agree, all of these, that at any given point, let's say X, what is the light coming from? What is the influence? Let's use the technical word because I think now you guys have gotten the intuition. What is the influence of point X1 on X? X1 on X is how much? Is proportional to e to the minus a distance between X1, X squared, leaving aside some proportionality constants. This is it, because I use the decay function. The further away you go, this is half the bell curve. I just happen to choose. It is called the kernel, by the way. You can choose other kernels, and we'll talk a lot about kernels. This is a kernel function. These decay functions are called kernel functions. So you took some kernel function, right? Or more broadly, you can say x I, x. Influence of the xi point on this is some kernel function xi, x, some decay function, something that decreases with distance monotonically, smoothly and monotonically. Any function you can take, but Gaussian is often taken as the standard. So would you agree that the point x1 will influence it to this extent, Rathik?
Yeah. That makes sense.
That's one. So now what about x2? So at point x, I will get the influence from f1, right, which is f2, fk. Suppose there are k points all around, isn't it? This one being fx1, x, this one being fx2, x, and so on and so forth, xk, x. This would be the influence from the kth point. So far, so good?
Yeah.
And so what happens if I am looking at the total influence at the point x? Would it be reasonable to say that this is the sum of all of these?
Yeah. I'm seeing that now. Yeah.
That is it. And the beautiful thing is that is not a function of the points anymore. That is just a function of where you sit, because the points are frozen, isn't it? The points, the data instances are data instances.
Yeah.
Because, and that's why I gave you the metaphor. Think of it that it is like reading a book and asking where there is more light from all the lamps, right? You change your location, lamps are not moving. You change your location, the light available there will change, isn't it?
Yeah.
That's it. And that's how you should think of the influence field. It's a scalar field. So one second. It's a scalar field. Obviously, light has directions, and so don't look at that. But you can think of it as the warmth from the lamp, right? So Albert, I'll come to your story. So there's a very interesting story, actually, a children's story that's told in India. It is called Birbal Ki Khichdi, right? It is the sort of the cooked food of Birbal. So apparently he was a wise prime minister to a king, or not a prime minister, but a very courtier to a great king named Akbar. And there are lots of stories on how Akbar will do foolish things. So I suppose I'll stop with this story that I think is appropriate, or may not be appropriate, maybe tangential, but for whatever it is, I think nice time to tell the story. So it turned out that there was a very cold, people were going through a cold winter. And Akbar just looked at a little pond or pond and said, my goodness, it's so cold. The water is freezing cold. Nobody can be in this water for more than 2 minutes, right? And people said, no, there are people who for food, they're desperate enough and they can do anything. So then you try it out. So he gave a competition. He says, whosoever can be in this freezing pond all night will get a huge reward, right? He will not be poor anymore, or something to that effect. I don't know how the story exactly goes. So then it turned out that a poor man came, a really hardy one, and he suffered through the whole night in that cold water, standing in the cold water of the pond. And next morning, he came out and he says, well, I'd like to have my prize now. So then somebody pointed out that, you know what, this is not fair, because some other courtier who didn't want Akbar to give him the prize, the poor man the prize, pointed out that there was actually a lamb a bright source of light, which was far off. And he says that this is cheating. That guy was not in complete cold. He was getting the warmth of that light far off, right? So, well, that's not fair because, how much warmth can you actually get from a light far off? So then Birbal countered, okay, all right, let's do one thing. Why don't you come to a lunch I'm organizing, a luncheon party that I'm organizing? Come, you'll have fun, to the king. So the king came, and Birbal said, well, we are still cooking the food. So the king was patient and said, all right. After a little while, king grew very impatient because there was no sight of food. And he asked, where is the food being cooked? And it turns out that in a very, very tall pole up there, 10 feet high, something like 100 feet high, there was a little pot containing the food to be cooked, khichdi. It's a dish, Indian dish. And at the very bottom of the pole was a tiny little flame. And Birbal said, well, look, I'm cooking the food. And the king said, how possibly can the warmth of this cook that food? And well, the story goes that then Birbal said, then how possible? But you said it can be, right? That guy got warmth from the lamp and you realized his mistake and so on and so forth. So it's a kid's story, of course. I am reminded of it because it brings home the point. You're looking at an influence field. Think of it as a warmth field, right? And so how much warmth are you getting from each of the points? Whatever it is, it's a quantity, it's a number. And you can sort of look at the gradient of it. You can go, if you want to quickly warm yourself on a cold night, what would you do? You would want to take the shortest path to the sources of warmth, to the sources of fire or something like that. And so what is the path that you would take? And where would you end up? Where you would end up, the warmest place, are your attractors. The path that you would take is the path of steepest ascent, hill climbing path, right? And all you have to find are these warmest, locally warmest places, the peaks around. Those are your attractors. Around them, you can create your little neighborhoods. Those are your clusters, warm enough. So one way to say, where does my cluster end? Cluster ends at the point at which it is warm enough, beyond which it is not warm enough, right? That's one way to think about it. Sort of a descriptive way to look at it.
As if you do gradient ascent, though, aren't you going to only hit one extrema?
Yeah, and so then you go to some other point and start all over again.
Oh, I see. That's why you're removing one of the clusters. Okay.
That's right. Now you're getting it. That's right. So it's a beautiful, Ratik. In fact, for you in particular, I don't know how many of you will do this project. Please do this, but Ratik, why don't you come back with the solution next week?
Okay, I'll try my best. Yeah.
Come bring back your notebook next week. I'd like to see you try it. Try it. You may or may not succeed fully, but see how far you go. A hint, it's very short code.
That's relative.
Let me put a number. It will be 100 lines or less.
No comments.
Yeah.
Without
Okay.
comments.
Yeah, without comments. Yeah. So, all right, guys. So with that, we end this topic. It is appropriate, about an hour gone. DENCLUE is lovely. You will really love it. It doesn't exist in scikit-learn. For all you know, guys, contribute to scikit-learn. If you want to. I don't know whether they'll accept it. Yeah, go ahead, Albert.
So those point 1 to k, those can be random, right? The amount of points that you want to choose.
Yeah. So what happens is set up your experiment. Take a random. If you have a huge data set, you can take a random sampling. Now these are your points, these k points here. And now you're working with those k points to find the attractors.
So it's some form of recursion function logic.
Why recursion?
You want to find the clusters, you just recursive around that thing.
No, it's not recursive. It's iterative. You take a k point. So let's say your data set size is k. When you're starting the learning, your data set size is k, right? And now you have a force field, which is the influence of all the k points. You do its gradient, and then you hill climbing. You'll end up with one of the attractors. You stop. Now, if you so choose, you can just remove the points that are in the cluster of the attractor. And then you start all over again from somewhere else, or maybe from the same point, whatever it is, doesn't matter. Okay. But no, recursive will call itself, right? It doesn't call itself. Any questions, guys?
There's some, don't need to discuss it in detail, but I guess a large data set, the final termination, that logic is complex, right? You have to
Yeah.
be able to say, I'm done searching. Because there is always possibility that somewhere else there is an attractor and you
That
will
is true.
go close to it.
That is true. So the point is that if you, that's why I use the eliminative process. And for me, it works, right? I'll have to look at the literature to see if it is strictly correct or not. But okay. See, here's the thing. When you have a massive data set, right? Can you use the force field argument? Yes, definitely you can use the force field argument. But the beauty of that on the entire data set, but why? Right? The beauty of density-based clustering is if it is really those dense regions, a subsample is good enough. Right? And so when you deal with a subsample, computations are fast. And not only that, you notice that you're working with gradients. So you're not computing the distances to everything. Right? You're just looking at the distances to those K points.
Okay. So there's an inherent concept of I have a large data set. I'm sampling from the data set to do a
Yeah,
parse,
you can do that. And
identify a cluster.
yeah,
Then I remove it from the large data set.
Yeah.
Whatever is around that cluster.
Yeah.
So that I've taken away all the points I don't want to look at again.
Yes.
Very quickly go through that.
Yeah, this is it. And so you can tell whether something belongs to a cluster or is an outlier. Right?
What's the
Either it
metric
belongs to
for?
one- Come
Oh,
again?
go ahead, go ahead.
Go ahead.
Okay. What's the metric for knowing when you have hit the attractor?
Gradient will disappear.
Oh, okay.
Yeah, at the top of every hill is flat. You know that.
Yeah, the gradient. Yeah, okay. That makes
At
sense.
least in the hills behind, in the what is it? Our Fremont area,
Mission Peak.
Mission Peak. Yes,
And so we're using ascent as opposed to descent because we're
ascent.
going to the top of a hill.
Exactly. And the same point. Remember, gradient points to the direction of greatest increase. So when you're ascending the hill, you go along the gradient, not opposite to the gradient.
Like the saddle point.
It's not the saddle point. It is truly the peak from every direction, maximum from every direction. A saddle point is a point like a horseback, where along one direction it's a minima and another direction is a maxima. Like if you think of a horse, right? Let's say a horse. How does a horse look? Well, this is my poor rendering of a horse. So if you're going along this direction, if you look at it, this point is a minima. But if you look at the circular direction, it is a maxima. In other words, you can fall off the horse, right? You're sitting atop this. This point is on top of the horse, right? So that's why it's called the saddle point. The word itself has come from horses. All right, guys, so let's take a break. We will have another hour of theory and then we'll break for lunch. Let's take 10 minutes and I'll see you in 10 minutes. Session. To summarize, in the previous session, we studied yet another density-based algorithm, DENCLUE. We realized that it's a pretty powerful argument based on it's a field theoretic argument. It says create an influence field. At any given point, there is an influence coming from all the real data instances, right? And that influence is a scalar field. It's a number, it's a field, it's a value, there's no direction to it. Now, given the field, if you take the gradient, you can take a hill climbing approach to find the shortest path to the peak of that influence, nearby influence. Right? And those peaks are called attractors. Then around the attractors, you can build your certain density region that you can take and say, well, that's where my cluster ends. And that is the only hyperparameter in the model. In practice, it works quite well. So that is the approach. Now, when you look at the influence, the question is, how do you do influence? What is the function? Any kernel function will do. What's a kernel function? Well, that's the topic we are going to talk about shortly. But for the sake of this one, take it as any decay function, means something that slowly decays with distance, right? So like Gaussian, half of a Gaussian is pretty good. One question that someone just asked is, why not 1 over r, right? That also decays with distance. You could, though people tend not to use 1 over r because it's computationally a little bit hard. What happens when the distance is 0? 1 over r begins to blow up, right?
Yeah.
It tends to go to infinity. Well, of course, then you can say, well, in the denominator, I'm going to add a constant value, alpha. So there are ways you can work. There are many kernel functions you can use. The most popular, obviously, is the Gaussian kernel function that you use. You can play around with some and see, but you should get essentially comparable results. That was DENCLUE, then a summarization of DENCLUE. The homework there was implement DENCLUE from scratch. I will give you a hint, guys. Go look at the code where we did linear regression from scratch. You remember we did linear regression? So we did gradient descent. And we did a process of iterating using gradient descent to find minima. You realize that this problem is almost identical to that. We are not doing gradient descent. The minus will become plus. In other words, in gradient descent, we used to do, what was the difference in gradient descent? In gradient descent, you would do beta next is equal to beta minus alpha, gradient of the loss function. Right. Whereas in this hill climb, in this particular one, in the DENCLUE, you're using the same argument, except that the next point you go to is the previous point plus, and you don't call it a learning rate. People often write it as delta, but it's exactly the same thing, gradient of the force field. Right? Do you notice how similar it is? So the code will be very similar. You can take an inspiration from the code, and therefore you'll realize that, especially with that code being present, it's a short exercise. Go use something, adapt that code, and you'll quickly be there. All right.